this worksheet, we're going to do an acid-base titration calculation. Just as a heads up before we get started, there are several different types of calculations that you can do for acid-base titrations. They all require a different problem-solving approach. This problem that we're going to look at involves a titration or a reaction between something weak and something strong. We're going to be looking at a weak acid reacting with a strong base in this particular example. However, if you had a weak base reacting with a strong acid, you would use the exact same strategy as what you'll see here. So this is for anything weak with anything strong. And then also we're going to be doing a titration calculation that focuses on the equivalence point of the titration. The equivalence point, as a reminder, and I'll talk about this a little bit more, the equivalence point is when the moles of the acid are equal to the moles of the base, the two chemicals in the titration. So the worksheet is going to be focusing on just this one problem right here. What is the pH at the equivalence point of 245 milliliters of 1.5 molar acetic acid being titrated with 0.8 molar sodium hydroxide. And that's the only problem that we're going to solve, and this is going to take you step by step through the solution process. So the first thing that you want to do when you're solving these types of problems is write a reaction write an equation for the reaction between the acid and the base. So whatever your acid is, whatever your base is, you're going to begin by writing a chemical reaction. Our acid is acetic acid, CH3COOH, and our base is hydroxide, OH-. And we've got to predict the products of this reaction, and we're also setting up the framework to make an ice table, although we're not going to fill it in just yet. Now you might be saying, where did this OH- come from? Because I can see here's the acetic acid, but what about the OH-? I thought we had NaOH. You need to remember that NaOH is an ionic compound that dissociates, and it dissociates into Na plus and OH-. And Na+, the sodium ion, is a neutral cation. It's in group 1A, which means it's neutral, which means it's not doing any kind of acid-base reaction because it's neutral. So in terms of the acid-base titration, it's the hydroxide ion. This is a base. The hydroxide ion is the one that's doing the actual reaction here. So we're not going to be writing NaOH. We're just going to be focusing on the part that does the chemistry. The products of this reaction are going to be CH3COO-, that's called acetate, and water. This comes from the acetic acid molecule donating one of its hydrogens. The charge goes down to a -1. That hydrogen gets transferred over to the OH- and makes H2O. So now let's work on filling in the ice table, and of course we want to start with the I row, and we know that initially we don't have any products, like that's pretty common in an ice table. What we do need to figure out is how much of this stuff do we actually have. So problem number 2, or step number 2, tells us to calculate the initial moles of the acetic acid. We're going to get that information from the volume and the molarity of the acetic acid. The problem tells us that our acetic acid is 1.5 molar, which means that we have 1.5 moles of the acetic acid, CH3COOH, per liter of solution. And the problem tells us that we have 245 milliliters, which is 0.245 liters. So this is how we're going to calculate the number of moles of acetic acid. 1.5 times 0.245 is 0.3675 moles. That is the initial number of moles. Also, because this problem is saying that we're at the equivalence point, and by definition, at the equivalence point, the moles of acetic acid are going to be equal to the moles of hydroxide. So we just know that these two numbers are equal to each other, again, because that is the definition of the equivalence point. That's what it means to be at the equivalence point. So with these problems, you're typically only going to have the information to calculate one or the other, and then you're just going to automatically know, because it's at the equivalence point, that these two numbers have to be equal to each other. So now let's get ready for filling out our change row. Because OH minus is a strong base, that means that this reaction goes to completion. That means we don't have a minus X plus X situation. We know that this reaction goes 100%. So in terms of our change row, we are going to react every single thing that we have. Instead of saying minus X, we know what X is. It's 0.3675. Also over here, we know what X is. It's 0.3675. We do want to make sure that we are paying attention to the stoichiometry of the reaction. It's 1 to 1 to 1 to 1. So that means that all of these numbers are exactly the same. And again, this is because it's a strong base. Even though this is a weak acid, that doesn't really matter. The strong base is controlling the reaction. The strong base, by definition, reacts to completion, and it's going to drag this acetic acid along with it in terms of reacting to completion. Now we can fill in the E row of the ice table the way that we normally do, just doing the math straight down each one of these columns. So we're going to end with no acetic acid, no hydroxide. We're going to end with 0.3675 moles of acetate and 0.3675 moles of water. And as you guys already know, we really can ignore the water. It's not going to be anything that we pay that much attention to. So when this reaction is done, we have 0.3675 moles of acetate and 0.3675 moles of water. Acetate, we've got to be thinking about acidity and basicity of our cations and anions. This is a basic anion. So we want to be, when we're writing these reactions, we want to kind of be thinking about this is a weak acid, this is a strong base, this is also a weak base. And water, let's just stop talking about water. So because we're generating, this reaction generates a basic cation, the pH of this solution is going to be dictated by this guy right here. This product that we're making, which is basic, is going to be controlling the pH of the solution. We need to figure out what pH is going to result from the 0.3675 moles of acetate that we generate. So how do we figure that out? This problem, basically what we want to kind of treat this problem now as asking, what is the pH of 0.3675 moles of the CH3COO minus ion? So we need to create another ice table. That's how we would solve this problem. We want to think about this base, acetate, CH3COO minus, being a base. That means it reacts with water. These are both weak, so this is now in equilibrium. This is a base, which means that it is an H plus acceptor, so it's going to be forming CH3COOH, acetic acid, and OH minus. This base reacting with water, generating OH minus, is where the pH of this solution comes from. We're going to make an ice table for this guy as well. This one's going to feel more familiar to you because this is very similar to ice tables that we've solved in the past. We've got some initial amount of this guy. We're not starting with anything over here. We've got to figure out how much of this we make because this is what we're going to use to calculate the pOH, and we're going to use that to calculate the pH. So how much of this do we have? Like, what exactly is there? Let's take a look at the next page. It'll help us figure this out. First thing we need to do, let's go back to this. We need to know what this number is right here. Now, currently what we know is that we have 0.3675 moles, but these ice tables typically are done in units of concentration. We could put the 0.3675 moles in here if we wanted, but it would be better if we could actually put this in terms of molarity. So let's get ready to calculate the molarity of the CH3COO minus. Now, we know that we have a certain number of moles, but what we don't know is the volume of the solution. So what we need to do is figure out the total volume of the solution. The total volume of the solution is going to come from our volume of acetic acid that we started with, and also the volume of NaOH. The problem told us, I'm going to scroll back, the problem told us the volume of the acetic acid, it was 245 milliliters. So we've got that, 245 milliliters, but the problem did not tell us the volume of the NaOH. And we have not yet calculated it. We knew that the NaOH was 0.8 molar, and also we calculated that we needed this many moles of NaOH, we can use those two pieces of information to get the volume. 0.3675 moles. I'm going to make a note of that. So we have 0.8 molarity, which means we have 0.8 moles of NaOH per liter. And that's the concentration of the solution. In this exact problem, we had I already forgot it, 0.3675 moles of NaOH. We don't know what the volume is, so we just need to solve for that number down there on the bottom. 0.3675 divided by 0.8. Our volume is 0.459 liters, which is 459 milliliters. And I'm going to double check that. I'm going to take this number and I'm going to divide it by my liters just to verify that I get 0.8. 0.3675 divided by 0.459 is 0.8. So this is our volume of NaOH. We'll add that to our 245. And our total volume, I'm going to do that in a different color. Total volume is 0.459 plus 0.245. Our total volume is 0.704 liters. I know I'm going back and forth between milliliters and liters, but hopefully you can keep up. Once we know the total volume, we're able to calculate the molarity of our CH3COO-. That's going to come from the moles of the acetate, CH3COO-, divided by the liters of that acetate. And the liters is what we just calculated, 0.704. The moles of acetate are right here, 0.3675. I hope you're keeping up. These problems are really, really difficult and really, really tedious. So be patient with yourself when you're working on them. 0.522 molar acetate. Now that we have this information right here, this is what we actually need, we can go to the back to our ICE table right here. So the initial concentration of the acetate, that's what we just figured out, is the 0.522 molar. And initially we don't have any of this stuff right here. Now let's look back at our instructions. We've got that done. Now we're going to fill in the change row. We're using X's because this is a weak base. We don't know how much it will react. So we're going back to what we're familiar with in terms of an ICE table, minus X plus X plus X. And at the equilibrium point, we're going to have 0.522 minus X, but we're going to assume that X is super small and it's just going to be 0.522 and X and X. And again, once we know X, this is what is dictating the pH of the solution. We'll be able to calculate pH. So we've got that done, we've got that done, we've got that done. Now we can write a KB expression for this. I'm going to write the KB expression over on this page, but then I'm going to copy it. Our KB expression is going to be our products over our reactants. Our products are being defined in terms of X, so it's X squared over our reactant, 0.522. So there's our KB. I'm going to take that over to here. And now what we need to do is just solve for X. We need to figure out what KB is in order to solve for X. The problem gave us Ka back in the beginning. This is pretty common. The problem gives us Ka, 1.8 times 10 to the minus 5. Ka is 1.8 times 10 to the minus 5. The relationship that we're going to use here is Ka times Kb equals Kw. So Kb equals Kw divided by Ka, 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. This is going to be 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 is 5.6 times 10 to the minus 10. We're almost done. Hang in there. Don't quit. We're going to plug this in up here for our KB, 5.6 times 10 to the minus 10. You've come this far, you can't give up now, we're almost done. Solve for x. 5.6 times 10 to the minus 10 times 0.522, and then take the square root of that. 1.71 times 10 to the minus 5. What does x represent? Let's go back to our ICE table. X represents OH minus. So we can use x to calculate the POH. POH is going to be the negative log of the OH minus concentration, which is being expressed by x in our ICE table. The negative log of x is 4.77. pH is 14 minus POH, which is 9.23. And we're done.